Question 21. Calculate the entropy change that occurs when 1 kilogram. So when 1 kilogram of water at 20 degrees Celsius is mixed with 2 kilogram of water at 80 degrees Celsius. Okay, so they want to know what's the entropy change. So what is the change of entropy? Okay, the way you go about doing this is first you find out what the final temperature it is that they will both reach, and then you figure out what is the entropy change by each one and add them all up. Okay, so in this case there is no phase change, there's only temperature change of the same phase of water. So basically the amount of change of heat from the 1 kilogram of water, 4190, is the specific heat of water going from 20 degrees to T degrees, which we don't know, but we can solve for it. That change in heat, delta Q, must be the same. The gain of heat must be the loss of heat by this 80, which in absolute value will be 2 kilogram times 4190 times 80 minus T. That will be a drop, so that they're both positive numbers. Okay, so we need to solve for the T now. So this is the change of gain is the same as the loss of the other. So 4110 cancels, so you have T minus 20 is equal to 160 minus 2T. So from that you can move these over, 3T is 180. Therefore, T is 60 degrees Celsius. So final temperature is 60 degrees Celsius. Now, that only helps you to find what the final temperature is. But to find the entropy, the definition of entropy is change in entropy is due to the change in heat at the temperature that is changing at. Now, this is assuming the change in heat is reversible. So often you will see the little symbol to remind you that the heat is supposed to be reversible. However, most practical situations, the loss of heat or gain of heat cannot be reversed. And that is usually one directional. But we have to use we have to assume that it is reversible and get a number. So usually that's the case. So in this case, we can only estimate or assume it is reversible. Now, if that's the case, the change of heat is really the mass, CV, and times the change in temperature, right? That is mCV delta T, but in terms of infinitesimal change will be this formula. So to find the total change in entropy, then you have to integrate both sides, which gives you the formula of NCV. So integral of dt over T is ln from low temperature to final temperature. So there will be ln T of T2 minus ln T1, which is same as T2 over T1. So that's a formula that we're going to use for this specific case in terms of change of heat without involving phase change. So for first part, which is from 20 degrees to 60 degrees Celsius, then let's find out what the change in heat is for the water, 1 kilogram water times the specific 4190 times ln. Now here is, you got to be careful. The T here is not in Celsius. The T here had to be in Kelvin. So T2, which is the final temperature of 60, is really 60 plus 273. And T1 initial is 20 plus 273. So for that, I'm going to get the change in entropy from the water from 20 to 60. But then the other one is from 80 down to 60. And let's call this 1 and 2. This is 2 kilogram one of 4190, but its final temperature is actually 60 also. So that will be 60 plus 273, but it started out with from 80, which is 80 plus 273. Okay, now we need to add these up. So all you have to do is punch in calculator and find out what each one is. 4190 times bracket 60 plus 273 close bracket divided by bracket 20 plus 273 close bracket ln equals, so the first one is 536. Now this entropy, so they will joule per Kelvin. And the second one is 60 plus 273 divided by 80 plus 273. And then I take a long on that, and then times 2 times 4190. So I get a minus 489 Kelvin. Therefore, the sum of all the entropy should be 536 minus that, so end up with 47.2 joules per Kelvin. 47.2. Okay, so I think the answer is 47.4, but that's probably rounding error. For question number 21 is 47.4. Okay, but that's probably just rounding error, so that should be fine. That's 21. 23 says, what is the entropy change of a helium gas of 0.130 kilogram of helium gas at the normal boiling point of the helium gas? Well, that means you got to look it up what the normal boiling point. The normal boiling point of helium gas, according to the table that you can look up or Google it, is 4.216 Kelvin. So they want to know like what is the entropy change of this mass of helium gas at the boiling point of this temperature when it all condenses isothermally to a liter of liquid. Well, that means it basically turns everything into liquid from gas. So that means we need to find out what the heat of evaporation and figure out what okay, so if you look up the heat of evaporation for helium, it happens to be 20.9 times 10 to the 3 joules per kilogram. 20.9 times 10 to the 3 kilogram. Okay, so if I have this much helium, and this is heat of vaporization, so for it to lose from gas to liquid, the amount of heat that it has to give up is the mass times the heat of vaporization, except in this case it will be a loss, a negative change. So delta Q will be this. But then change in entropy will just be the temperature that the loss occurs at, which is a boiling point of 4.216 Kelvin, and this is correct unit. And that's in joules, that's in Kelvin. So 0.130 negative times 20.9 to the 3 divided by 4.216. I get a negative 644 joules per Kelvin. And negative 644 joules per Kelvin is the correct answer. Number 25. So number 25 says calculate the change in entropy when 1 mole of water, which is 18 grams per mole, at 100 degrees Celsius, evaporates to form vapor at 100 degrees. So this is from liquid to vapor, also 100 degree vapor. So they want you to figure out the change in entropy of 1 mole of water. Well, 1 mole of water is 0.018 kilogram, and the specific heat for water is 4190 joules per kilogram Kelvin. So you multiply these two, and that will. Oh, sorry, that we're not talking about the change in temperature within the same phase. We're talking about a phase change, which means that we need to look up the heat of fusion for water, which is 2256 kilojoule per kilogram. So if you multiply these two, you get the amount of heat required. So that is your Q, which is basically mass times heat of vaporization in this case. And then you divide it by the temperature that this is done at, which is 100 degrees Celsius, but you got to convert that to Kelvin, okay? Do not use Celsius there. You got to convert that to Kelvin. So 0.018 times 2256 divided by 373, I get a number of 109 joules per Kelvin, and that's correct. So that will be for water. And number 25B says repeat the calculation for 1 mole of liquid nitrogen. So 1 mole of liquid nitrogen, okay, and 1 mole of silver, and 1 mole of mercury. So I need to look up the table for all the molar masses of each one of these. Nitrogen is 14, so times 2, so 28 grams or 0.28 kilogram. Silver, according to periodic table 108, so 0.108 kilogram. 1 mole of mercury is 0.201 kilogram. I multiply by their heat of vaporization. Now for nitrogen, heat of vaporization, look up the table, is 201 kilojoules per kilogram. And for silver is 2336 kilojoules per kilogram. And for mercury is 272 kilojoules per kilogram. Now all these will be the change that you need to gain in heat, but then divided by the boiling point where they're changing the phase at. For nitrogen, liquid nitrogen, the boiling point is 77.34 Kelvin. For silver, boiling point is 2466 Kelvin. So these are all in Kelvin by looking up the table. And for mercury is 630. And then if you calculate this calculation, you should end up with 72.8 joules per Kelvin. And this is 102 joules per Kelvin and 86.8 joules per Kelvin. So that's 20. Okay, the temperature is 25 degrees Celsius. Convert that to Kelvin is 298 Kelvin. So they want to know isothermal expansion of an ideal gas 2 moles from V1 to V2 at a temperature of 298 Kelvin. But the amount of work done for isothermal expansion is really nRT ln V2 over V1. Remember that was the work done, which is the only, which is the same as the heat for isothermal expansion. So you got to remember this formula. And therefore the work done, which is the heat, in this case should be 2 moles, 8.31 for R. Temperature is 298. ln V2, which is 0.0420 divided by V1, 0.028. All that divided by temperature for the change in the entropy. Now these two cancel anyways. So we have 2 times 8.31 times 0.0420 divided by 0.0280. Take a ln. I get 6.74 joules per Kelvin. 6.74 for question number 25. 27. 6.24 for question 27. 6.747 is correct. So that's how you do it. Number 27. Number 29. Number 29. 2 moles of ideal gas N. 2 moles of ideal gas occupies a volume of V. The gas expands isothermally and reversibly to a new volume of 3B. So from V to 3B. Part A, is a velocity distribution changed by isothermal expansion. Isothermal means there's no change in internal energy because delta T is 0, which means that if there's no internal change in energy, then the velocity, which is a form of measuring temperature, distribution should not change either. So is the velocity distribution changed by isothermal expansion? No. So part A should be no. Part B says calculate the change in entropy of the gas. Calculate change in entropy of the gas. Now this is isothermal expansion, so we could use the same formula as before, is nRT ln V2 over V1. So in this case it's 2 moles to 8.31 for R. Temperature in this case, do we know the temperature? Well, whatever the temperature is, we're going to divide it by T anyways. So this T disappear, and ln 3, because it's 3 times the initial, so V2 over V1 just 3. So all you have to do is multiply 2 times 8.31 times ln 3, and I get 18.3. So for question 29, I get 18.3 joules per Kelvin, and that's correct. So then part B and part C says, use another formula of 18.18 to calculate the change in entropy of the gas. That formula basically says use the Boltzmann Constant. Okay, that is delta S is same as the Boltzmann Constant times ln of W2 over W1. Now W stands for the number of possible microscopic states for a given macroscopic state. Well, if you increase the volume, okay, everything else being the same, like the temperature being the same, then the number of states should also triple because you've tripled the volume. So the number of states would triple if you increase the volume only. In this case, temperature is the same. So this will be K times ln 3. But what's K? K is what they refer to as the Boltzmann constant, which is the gas constant per mole. Okay? That's gas constant per mole. And the number, Boltzmann constant, well, gas K is really R divided by Avogadro's number, which is same as 8.31 divided by 6.02 times 10 to the 23 anyways. So that's what is in front of it, but this will be per mole. So if I have 2 moles, I multiply by 2, right? So 2 times 8.31 divided by per mole. So if this is per mole, and then I need to multiply 2 by the Avogadro's number in order to figure out total number of molecules. So 2 times the Avogadro number is total number of molecules. This will be per molecule. So 2 times Avogadro number is that many molecules, multiplied by the Boltzmann constant, which is the basically the energy per molecule. So if you divide the 2 Avogadro's number, you just end up with 2 times 8.31. Well, that's exactly what we did before, and then of course multiply by ln 3. So we basically end up with the same number, 2 times 8.31 times ln 3. Okay, except this would be from the macros calculation, but this would be from the micros calculation using the Boltzmann constant, but they end up being the same anyways. So it should be 18.3 joules per kilogram. Per Kelvin. So that's number 29. Number 31. So let's do number 31. Number 31 says, you have a solar heating in winter. A well-insulated house has 150 square meter floor space, but requires 1.50 times 10 to the 10 joules of heat for the month of January. Well, if it's for the month of January, I assume that there are 31 days. So the heat is to be supplied by a solar collector with a collection efficiency of 60%. Okay, so efficiency is 60% from the solar collector. The average solar energy input in January is 65.7 watts per square meter. Well, that is the amount of sunlight hitting the panel. Okay, is 65.7 watts per square meter. And then they ask, what area of a solar collector do you need to meet the requirement? So, well, let's see. If this is how much sun you get per square meter, okay, and this is how much energy you need in January. So let's figure out how much energy you need per second, because that has to do with watts, and that's what watts is. So 1.50 times 10 to the 10th joules. This is basically per January month, right? So you divide that by number of seconds in a month, which is 31 days times 24 hours times 60 minutes times 60 seconds. So this will be now in seconds. So if you divide all that, let's see what we have. 1.5 to the 10 joule divided by 31 days divided by 24 hours divided by that, we get 5,600 joules per second, well, watts. Okay, that is, we need 5,600 joules. Watts. And the sun gives you 65.7 watts per square meter. Okay, but we only get 60% of that light, so we can figure out how much watts we are actually getting by multiplying by 60. So we have 65.7 times 0.6. We are really only getting 39.4 watts per square meter, but I need 5,600 watts. So this divided by that will give you number of areas. So the area would then be 56 watts divided by 39.4 watts per square meter. Then the answer will be in square meter. So I get 142 square meter. Okay, so that is how much area you must have, at the least, to meet the requirements of 1.5 times 10 to the 10th joule for the month of January. But you have an area 150, so this should fit under the rooftop. They say that, or the floor space of whatever the rooftop is, 150 square meter. So this will fit into the rooftop of 150. So the answer is 142. That's correct. And yes, you can fit under the rooftop. So that is the rooftop area. Okay, number 33. Number 33 says the roof of a suburban house is equipped with 8 square meter of solar panel with efficiency of 60%. Well, if you have 8 square meter with efficiency of 60%, then you really only have 4.8 square meter. Okay? Used to heat the water from 15 to 55 degrees Celsius for household use. So you really have this much area that is providing energy to warm up the water from 15 degrees Celsius to 55 degrees Celsius, which is a change of 40 degrees Celsius. Now, if the average solar input is 150 watts per square meter, what is the volume of water that can be heated per hour? So if the solar energy input is 150 watts per square meter, and effectively I only have that, so multiply these two will tell you what watt you are getting. So 4.8, and then you get 150 times 4.8, you're getting 720 watts. 720 watts in 1 second is 720, in 1 second is 720 joules. But what about 1 hour? 1 hour is equivalent to 3,600 seconds, so times 720 watts will give you an energy of 2.592 times 10 to the 6 joules. That is in 1 hour. So in 1 hour you get that many joules from the sun, and you are going to heat that up, or you're going to heat the water up by 40 degrees Celsius. So mCV delta T equals to this energy Q. So mass would therefore be Q divided by CV, and delta T is 40. So Q up here, CV is 4190 joules per kilogram, and times 40. So if I divide this by 4190 divided by 40, I get 15.4 or 15.5 kilogram. Now, water, 1 kilogram of water is same as 1 liter, okay? Because the density is 1, really. So, therefore, the volume we're talking about is 15.5 liter, okay? Because for water, 1 liter of water is same as 1 kilogram. So, for part 33, now we've got to be careful here, because when they say 8.0, they only gave 2 sig figs, so I cannot use this one. Now, I'll probably use 16 liter if I look at this number for 2 sig figs, but I think the answer is only 15, right? The answer is 15, but I got 16 because oh wait, let me see. What was the number? 2.592 to the 6 divided by 4190 divided by 40. Oh, I see. I get 15.4. Okay. So if I round it off, 15.4. So if I round it off for 2 fixed, it will be 15. Okay. So 15 liters. So that much, the 15 liters could be heated up within 1 hour. During the average day, a typical household uses 75 liters, okay, at 55 degrees Celsius hot water for each person. So each person, a typical household uses 75 liters, okay, of hot water for each person. How many inhabitants? So during an average day, a typical household uses 75 liters of this hot water at 55 for each person. So each person takes 75 liter, okay, per person. So how many inhabitants can this accommodate? Well, that is during an average day, but this is per hour, right? So all we have to do is multiply this one by 24 hours. So if I multiply this one, this is per hour, multiplied by 24 hour per day, I get 15 times 24 hours. Oops. 15 times 24 hours. I get 360 liter of hot water. Okay, so okay, and then each person uses 75, so 360 divided by 75, I get 4.8. So if you round it to a single digit, that'll be 5 persons. Now remember, this is this number given to you earlier, that is 150 watts per square meter. That is on average. Okay, that is, they have already taken all the daylight time power divided by 24, because there is no power at night, and that will come down to average of this. Obviously, during the day it will be much higher than 150, but they average it to 150 over 1 day. So here, that's why we could actually also multiply the 15 liter by 24, assuming that this energy input is steady and even, but in reality it's not. So anyways, so this is how you do it. So the answer, number 33, is 15 liters and 5 person. Okay, so that's how you do it. And then number 35. 35 says, a solar house has a storage facility for 4.00 times 10 to the 9 joules. Okay, so this is a solar house which has to store 4.00 times 10 to the 9 joule of energy. Now, if we want to build a space to accommodate this much energy, but using water to hold the energy, how much volume would it require? Well, water is assumed to have a 21 degrees Celsius first. You can raise it to 49 degrees Celsius, okay, with this solar house. So they say that if this is the case, water at regular temperature 21, but can be increased to 49 after the sun shines on it. So how much water would be required so that this much energy can be held? So that's basically mCV delta T equals to that Q. So M is simply Q divided by CV delta T. So Q is this number, 4.00 times to the 9. CV is 4190, and the change is 41 is 28. Okay, the difference is 28. So all you have to do is punch in the number. So I get a mass of 34094 kilogram. Now kilogram is, as I said, a kilogram in the density of water is, there is a 1,000 kilogram in 1 cubic meter. So if I divide it by 1,000 kilogram per cubic meter, then I really just have 34.1 cubic meter. Okay, so that's all you have to do, is divide the volume by the density of water, and that's the correct answer. Now, but if you use water to hold this much energy. So let's change the material. Part B says, if you now start using, instead of water, you use the energy stored, or you store the energy in something called Glauber salt, which is basically sodium sulfite crystals, sodium sulfate crystal. If you store the energy in Glauber salt, okay, in the same temperature range, then how much volume would you need? Okay, so they do provide some data. For example, the specific heat for the Glauber salt, okay, let me just write down as salt. The specific heat, CV, in solid is 1930 joule per kilogram Kelvin, and if it was liquid of this salt is 2850, okay, and then the density of this salt is 1600 kilogram per cubic meter, and then the melting point is 32 degrees Celsius, and heat of fusion is 2.42 times 10 to the 5th joules per kilogram. Okay, now here you gotta be careful here, because you notice that their melting point is only 32. If it's 32, if it's only 32, that means that the solid will go through a phase change in order to reach 49. So in your mind, you have to think about this, is that at 21 degrees Celsius and 49 degrees Celsius, whatever the mass you're thinking of this salt, will have to go through a phase change at 32. Okay, here's a phase change. And when there's a phase change, there will be extra heat required to melt it. So there are 3 steps we need to calculate the amount of heat that will add up to this amount. Okay, so Q really consists of, let's assume the mass is M. We don't know, we have to figure out. M of this salt is raised from 21 to 32. So M CV, this is solid phase, which I will have to use this number, 1930, raised to a temperature of 32 minus 21 from here to here. Then I have to go through a phase change. So heat of fusion is M times this number, 2.42 times 10 to the 5. Now it is in liquid state. Then I have to go and raise the temperature from 32 to 49 in liquid, which means 2850. So 2850 and times the change of 49 minus 32. So all that equals to Q. So let me just figure out exactly how many M's I'm talking about. Okay, so let's say 1930 times that's 11 plus 2.42 fifth to the 5th plus 2850 times the difference of 49 minus 32. I get a total of 311680 equivalent Q. So Q divided by 311680 should give me the mass. So take that number, I divide it by, or take this number 4 to the 9th divided by what I just found, and I get an M is 12833 kilogram. 834 kilogram. But we want the volume, not the mass. So that's where the density comes in. The density tells you that every 1600 you get 1 cubic meter. So you have this many kilogram. So mass divided by the density gives you the volume. So 12834 divided by the density of 1600 divided by 1600, I get 8.02, but I can probably just say 8.0 cubic meter now. So obviously compared to water, water will require 34 cubic meter space to hold this amount of energy, but that salt only require 8.0 cubic meter, far smaller than that. Almost a quarter size of that. Okay, and that looks like it's correct too. So that's how you do number 35. And 37. Says electric versus conventional automobiles. Consider an energy conversion process that involves 2 steps, such as using heat to boil water and using the steam from the boiled water to turn an electric generator to generate electricity. Each step has its own efficiency. So is the efficiency of the overall process equal to the sum of the 2 efficiencies, or the difference, or the product, or what? Well, obviously it should be the product, because whatever the second step efficiency is from the leftover from the previous step. So what used to be the input, or what used to be the output from, say, burning the fuel, becomes the input to the next stage of kinetic mechanical conversion. So it should be the product. Okay, efficiency, you always multiply the efficiency to get the overall efficiency from the beginning to all the way to the end. Obviously, you cannot add the efficiencies. Otherwise, 50% of first stage and 50% of second stage would mean the whole thing will be 100%. No, that doesn't make sense. Okay, so therefore, the answer for part A is just product. You multiply all the efficiency together to get an overall efficiency. Okay, so part B, conventional automobiles are about 15% efficient. This is conventional automobile, meaning that you take the gasoline and you burn it to convert into a moving vehicle. So only 15% of the energy released by burning fuel is eventually converted to kinetic energy of the automobile. Okay, so that's what they're stating. However, in an electric automobile with a battery-powered motor, well, the energy of the car actually comes from a power plant, okay, meaning from your hydro company, or from a socket of the wall, or on the wall. But the energy from the power plant that supply you electricity, that they have to get the electricity generated somehow themselves, okay, so that you can plug into the wall to get your battery charged. So if the efficiency of an automobile can be calculated. Okay, so they say calculate the efficiency of an electric automobile using the following data. Now remember, the efficiency of the overall is always the product of efficiency of each stage of the energy conversion. So stage 1, he says, a typical electric power plant has efficiency of 40%. Well, okay, so 40% is the first stage. Whatever, maybe converting, the energy of water, of the fuel, burning, and then burning the fuel in order to boil the water, and then the water turns the turbine, and the turbine turns the generator, and then eventually the electricity output is 40% of the energy input. Second stage says 10% of the energy supplied by the power plant is lost. Well, if 10% is lost, that means the 90% is going on to the second stage. And then step 3 says 10% of energy received by the city is lost in the distribution within the city. So this 10%, the first 10% loss was from the power plant to the city in the middle of the transmission, along the highway or something. But the second 10% loss is in the distribution within the city, which means that by the time you get to your home, you only get 90%. And then they say the efficiency of the battery charging process is 80%. That means from your wall socket, okay, going through a battery charger, your car is actually only getting 80% of the energy from the wall. And then last stage, the efficiency of the electric motor itself is 90%. So how is the overall efficiency of the electric motor or electric car compared to the conventional car? So we multiply all these together and see what you get. So 0.4 times 0.9 times 0.9 times 0.8 times 0.9, I get a 23% efficient. So the efficiency for the car, number 37, is 23%, which is still better than 15% of the automobile. So the efficiency of the electric car is still better. Okay, 37.